Hey everyone, and welcome to this explainer. Today, we're unpacking an incredibly simple geometric shift that is about to completely revolutionize electric vehicle performance. I mean, if you think the electric cars of today are fast, efficient, and technologically advanced, well, you haven't seen anything yet. We are looking at a fundamental redesign of how an electric motor is actually shaped, and the results are frankly staggering.
All right, let's jump right into Section 1, the ultimate power record. So recently, a UK-based company called YASA, who are actually part of Mercedes-Benz now, announced a prototype electric motor that hit an absolutely unprecedented peak power density of 59 kilowatts per kilogram. I want to let that sink in for just a second. That is roughly triple the power density of today's top electric vehicle motors. Most automotive motors typically sit somewhere around the 15 to 20 kilowatts per kilogram mark for peak power. So hitting 59, that's just a completely different universe of engineering.
To put that insanely high number into physical perspective, just imagine 1,000 brake horsepower motor sitting right next to an everyday, standard Coca-Cola can. It literally occupies 80% less volume than traditional units. This gives designers just an unprecedented amount of freedom, because this motor takes up barely a third of the traditional space.
The scale of this breakthrough is just staggering. Standard, top-tier EVs max out at around 20 kilowatts per kilogram. Even a nitromethane top-fuel dragster, a vehicle that is practically exploding its way down a track, hits about 30. And then boom, there's the YASA prototype at 59. Now sure, as some analysts have jokingly pointed out, it's still chasing the 153 kilowatt per kilogram space shuttle turbopump. But for a terrestrial vehicle, there's simply no comparison.
Moving right along to Section 2, radial versus axial motors. We can kind of frame the whole core of this explainer as an epic showdown of shapes. On one side, you have the traditional elongated, heavy, sausage radial motor. And on the other side, the revolutionary, ultra-thin, pancake axial motor. You see, in standard radial architectures, the magnetic flux travels perpendicularly to the axis of rotation, and that requires long, heavy copper coils and thick rotors. But in the YASA axial flux motor, the electromagnetic flux travels parallel to the axis of rotation. It's essentially this brilliant, flat, circular sandwich design.
Which brings us to Section 3, the physics of pancake power.
Now you might be wondering, why in the world does simply flattening a motor into a disc unlock such massive, record-breaking performance gains? How does one single physical transformation completely rewrite the rulebook on the dynamometer?
Well, the crucial point lies right here in the definition of torque density. If we think back to basic physics, torque equals force multiplied by radius. By taking those permanent magnets and moving them further out from the center axis, meaning you're increasing that radius, you naturally multiply the torque. It's exactly like the leverage you get from using a much longer wrench. In a traditional radial machine, you just can't do this without making the motor ridiculously heavy and bulky. But because of this pancake topology, engineers can actually completely remove the stator yoke. You know, that heavy iron ring usually needed to guide the magnetic field. Suddenly, there is zero wasted space inside the rotor for electromagnetic purposes. This translates to an incredible 80% less stator iron mass. The whole motor is 50% lighter and only 20% the depth of a typical radial machine. And yet, thanks to that leverage we just talked about, it delivers up to 800 Newton meters of torque. That's literally 4 times the torque density of other EV motors.
Okay, let's jump into Section 4, beating the heat problem.
As any engineer will tell you, extreme power generates extreme heat, making thermal throttling the true, absolute worst enemy of any electric vehicle. While standard radial EV motors suffer from heat getting trapped deep in the stator, which forces the electronics to slash available power by up to 50% when pushed, axial motors are totally different. They guarantee a massive 75% continuous power relative to their peak. And the secret to that? It's all in the cooling architecture. Because the copper windings in an axial motor are so much shorter and they're segmented, cooling oil can actually be injected right into direct contact with the stator's copper coils. What that means is endlessly repeatable performance without overheating and losing power, even if you're doing launch after launch on a track.
All right, let's look at Section 5, the supercar revolution.
Mercedes-Benz is fully leveraging this exact pancake geometry for their upcoming AMG high-performance electric architecture known as AMG.EA. By packing in 3 of these YASA axial motors, built right over in Berlin, by the way, these test vehicles are churning out an astonishing 1,169 horsepower. They are launching heavy, luxury four-door coupes from 0 to 100 kilometers per hour in a blistering 2.1 seconds. It's absolutely wild.
And hey, it's not just quick off the line. Over at the legendary Nardo Ring in Italy, an AMG prototype was put through some seriously extreme endurance testing. We're talking running for over 40,000 kilometers at constant speeds of around 300 kilometers per hour. Just think about the thermal load that generates. Yet, even with outside temperatures pushing past 35 degrees Celsius, that direct oil cooling kept the stators and rotors in perfect thermal operating windows, with zero degradation in performance.
Even the legacy supercar builders, who are incredibly dedicated to internal combustion, are jumping on board here. Companies like Ferrari and McLaren were actually some of the first to realize the true potential of these ultra-flat modules. Because they're just millimeters thick, they can be seamlessly squeezed right between a screaming combustion engine and the gearbox. This gives models like the SF90 Stradale and the McLaren Artura hundreds of newton-meters of instant electric boost, all without even having to lengthen the wheelbase of the car.
So that brings us to the ultimate takeaway. If a motor taking up 50% less volume and weighing 50% less can completely redefine a $1 million supercar, what exactly happens when manufacturing scales up to normal cars? Because 50% less weight means automakers can use smaller brakes and smaller batteries while achieving significantly more range for our everyday commutes. Plus, fewer materials like iron, copper, and magnets make it a far more environmentally sustainable product across the board. I want to offer a massive, massive thank you to all of you, our listeners, for joining us on this explainer today. We've unpacked the physics, the showdown of the shapes, and some truly unbelievable performance records. But as we wrap up, I want to leave you with this to ponder. When the electric motors powering our entire world shrink from the size of watermelons down to the size of a frisbee, what else will we be able to electrify next? Keep learning, keep questioning, and I'll catch you in the next explainer.